tonight is very special because it's another person from Braid, a person that I've actually known for quite a long time. We've been working together kind of on and off since 2020.
Something like that.
Something like that, yeah. So we met at Woven, and we were not on the same team, but we ended up kind of collaborating. We connected over Rust. I still remember the first lunch that we had together, and I told you that I really liked chicken nuggets, and you told me that in the Netherlands chicken nuggets were for babies. I thought that was hilarious. Anyway, so Sjors has a background originally in aerospace, and then he spent a lot of his career working on maps. If you use Google Maps or Apple Maps, raise your hand. Yeah, there's probably some data in there that went through machinery that Sjors worked on. So please give him a very warm welcome.
All right, yeah, thank you. So tonight we're going to talk about a bit of fun with geometry in Rust. Does any of you have experience with working with geometries, either in architecture or product design or game engines? Two, three, four, quite a couple. First, a heads up. When I mean a bit of fun, that means literally every time I'm talking about bits, that's more of an optimization that's not really important. Everything else is more the important part. But as Mate mentioned, we're going to be talking about mapping. The goals of this presentations are: what is mapping? What is GIS, Geographic Information Systems? But mostly, if you are working in a company, geo company, thank you, in a geo company, what are the key tech choices to be successful? How can you determine where you are, and how can you grow to become better and build your own ecosystem of high quality libraries and tools? And we're going to do that, of course, by showing some algorithms and data structures throughout this talk. So first, explaining what mapping is. Generally what we do is we capture data with mobile vehicles or satellites or planes, and we capture the real world. We enrich that data, make it more rich in information and make it more unstructured, and then we distribute it so that people can do analysis. So they can determine how many solar panels can fit on my roof and where should I place them, to what can I see from my window, are there water pipes in the ground here, can I dig here, many of that kind of information. Should I dig here for oil? So in general, we'll have vector data. Vector data means points, lines, so lines, linear segments between 2 points, or polygons, for which I'm now, for this talk, just going to simplify them to rings, so a closed ring of a line that forms a closed ring. There's also a lot of raster data, so you just have pixels that indicate, okay, this pixel is water, this pixel is a house. It's part of mapping, but not the topic of this talk. But who am I and why am I talking about this? Mate gave you a little bit of an introduction, but I started with my education working on architectural models. And architectural models are very detailed, made by humans, and they have many small pieces of walls and their furniture. And what we want to do in mapping is we want city models. So very wide range data, countrywide, globally. So, and we want to optimize this data for analysis. That means when we're dealing with hundreds of thousands of buildings, we don't want to have to fix tiny errors of how they were created at every model. The algorithms need to be perfect. And they also need to not contain too much information. So generally, we're only interested in outer shell. So that's what I did here. You may also have seen them being called smart cities or digital twins. I don't know what's really the difference. They're all just different buzzwords. They'll probably bring a new buzzword for it in the next years. I went to Sweco, Swedish consultancy, but It's in the Netherlands. And in the Netherlands, there's a lot of open data. So all the data that the government is using is also available to the public. And we would build the software to generate and maintain this data. So the BGT is a base layer map of the Netherlands. It's maintained by hundreds of organizations, all together in one map, making edits every day because the data needs to be up to date for 3 months maximum. It's very accurate, so at centimeter level, but of course if you have water it's not that accurate. And after that I went to Woven by Toyota and I worked on self-driving vehicles. So again, mapping, now we just have lines and it's a safety critical situation, so the data needs to be perfect. Basically how it's used is we have a car driving around seeing the real world, and it locates itself into the map where it is, and it has this map like on the vehicle, so it can get extra information on it. Like, even though I don't see this wall in reality, but it's in my map, so maybe slow down and try to make sure that there's no hazard there. So now, what that actually means, like you can see my career going from 3D objects to 2D objects to 1D. And now I'm in Braid, and it's just implied geometry. But there's one thing in common between all of these, and that's for each of these situations, there's a common algorithm where we're extracting the boundary. So we're extracting the exterior shell of this building. Or in the 2D polygon case, we need to make sure it's a perfect cover. And I will go into more detail during this talk. But basically, we don't want to have any gaps, and if you make a gap between 2 polygons, that's the exterior of the combined set. Similar to the case with the HD maps, where we have lines, and lines need to be perfectly connected because you don't want to be surprised when the vehicle is, and the road suddenly stops, kind of thing. So we need to really make sure that we validate that all the edges are perfectly connected and that the exteriors are at the beginning and at the end. So today we're going to mostly be talking about the 2D case because that's like easy enough to understand, but also interesting enough. So what this map is made of is like basically we're mapping everything at ground level. So we're measuring a section of grass that has to be mowed in one direction, but also a lot of metadata. So the road, we will say like this as a function of a local road. It has tarmac, so a lot of metadata. And that way, we create this entire perfectly connected set of polygons at the ground level. So a bridge is not ground level, the water is ground level. So yeah, we create this perfectly connected set, optimized for analysis. We know that there are no gaps, but how we know that there are no gaps is because of the algorithm that we're talking about today. So to explain the problem, if we have these 2 polygons here, the yellow one and the green one, the yellow one has an extra vertex. When there's a point or vertex or a coordinate that's not exactly matching with any other coordinate, we just consider it's not connected at all. Meaning that between the green and the yellow one, there's a tiny sliver of a triangle. It doesn't matter how large it is. It's not connected, there's a gap. So we can't rely on algorithms to know that these shapes are connected by an edge. We also need to distinguish gaps from holes. So there's an interesting situation here in the Netherlands where there are actually pieces of Belgium, like areas of Belgium in the Netherlands. So this is a Dutch city of Balen with pieces of Belgium just stamped out. And yeah, that's situations we need to deal with. It's exterior.
There's so much water, right? It's like
Last thing, we need to deal with overlap. So this Japanese input here, where we have the nori overlapping the onigiri rice. And that's also not okay. Like the map is defined to be perfectly flat and complete. So further definitions, when I'm talking about polygons, I'm also just mostly going to refer to them as rings. So a polygon has an exterior ring, but can also have interior rings. So the exterior goes counterclockwise, the interior will go clockwise. That's not important for the rest of the talk. They're all just rings. But for now, for simplicity, we're just going to focus on things with one ring. So, for example, what we want to do is, remember, we're having 200 organizations updating a map at the same time. So we need to make sure that we don't trip on each other and conflict with each other. So you might want to have a city is renovating an intersection, changing it into a roundabout. So we have this current map, and we want to know the outline of it, what's the exterior. And we can generate that, and we'll map our new roundabout, and that's our new geometry there on the right. We want to have this to be the exact same exterior outline so that we can say, okay, this area is locked, and we can replace it without stepping on other users. All right, last piece of the puzzle. So I mentioned this countrywide. We also have maps that are a global scale. Generally, what's a very recurring number is somehow 200 gigabytes. So to me, that's not big data, but it's also not small, right? It doesn't fit in your memory. So you have to do optimizations, and you have to at least care to not be slow. Generally, what you find, because it doesn't fit in memory, is that performance is going to be driven by the speed of your drive. So we'll end up, like when you think 200 gigabytes, we need to process all this data. So when you have like a 50 gigabyte Blu-ray of your game, generally you're just looking at a small portion at the same time. Here we're generating all of it in a small amount of minutes or seconds. You'll measure it in seconds. Or weeks if you do it wrong. So how do we get to that performance? By Chandler Carruth, he says efficiency with algorithms, performance with data structures. So that's how we structure this talk. And so this is the question I'm going to ask you. We have two triangles. They're connected to each other. We have the triangle ABCA and the triangle ACDA. And we want to extract the exterior ring for these two geometries together. Right, so you see a gap now between like the AC edge that there's no gap there. It's just two geometries. Does anyone have an idea or a suggestion on what the algorithm would be to extract this exterior ring?
Perhaps something that would get the largest area between the points?
The largest area between all the points. So the largest area between all the points, you would get basically the convex hull. And if there's like a dimple in your shape, you would not get it. But nice try. Another one?
The idea would be to try to figure out that AC and CA are the same thing.
Yes.
So you would have like an algorithm that go like, is AB among these AC, CD, DA, or if BA is in AC, CD, DA, and do that all the time. Or
That's exactly the right direction. We want to know that we want to count AC, right? We know that AC occurs twice, and all the other edges only occur one time. So that's how we can determine that. Is that the direction you're going also?
yeah, you need to use a set, I guess.
So how do we do that? There's one more addition that I want to add, is that we actually need to orient the segment. So now we have a segment that is CA, and we have a segment that's AC, because all the polygons are counterclockwise. So the first step is to orient them, so that both of them are in the same direction. And then we can either use a hash map or a vector. We're going to use the vector because the vector is better. The C++ standard says so. It's generally more interoperable and such, and I hope after this talk you'll understand what. So we'll end up with these flipped segments in a large array, and we're going to sort them. Sorting them means that A and C, like I sorted them alphabetically because, are now together. So if we now group by segments that are the same, you get groups of 1, most of them, and 1 group of 2. So if we use all the groups of 1, we'll find the solution. But there's a reason why I put a prime mark there as well, because there's an edge case that we need to support, where if we have 3 geometries that are overlapping on the same green square, you might count them, right? And you get nice 1, 1, 1 for the exterior boundary, but we have overlap, and like, we get 2 for the interior boundaries. So you think like that's perfectly nicely connected, just like the previous one. But the difference is, because of this weird construction that we have going on, is that the edges are going in the same direction. So actually what we need to count 1 segment should be flipped and 1 segment should be unflipped. And that's how we determine, okay, this is definitely a normal interior boundary. Now, we're getting to the point that we're getting, why we're here, like the Rust part. Frequently there are Rust beginners here, so here are my recommendations. Don't write macros, don't write unsafe, don't write async. I think that nobody is too much against that. Don't write lifetimes. Generally, when you find yourself writing lifetimes, you're doing it wrong. Make it simpler. But maybe more controversial is don't write traits and don't write impl functions. When you write traits, just write struct. It's fine, just data. Okay? So do write structs, enums, and free functions. Mate said, like, hey, that's like Haskell. Like, no, functions should return data, not functions. Okay. Okay. In general, your program should be just arrays and functions that loop over arrays, and then you're good to go. So, efficiency with algorithms. So, the algorithm was 2 parts, right? We had 1, extract all the boundary segments, and the second part of the algorithm is turn all those boundary segments into rings again. Let's look at extracting the boundary segments. Fairly straightforward. For all the rings that we get, we just want all the segments. We're going to sort them, like we said before, and we are going to extract the exteriors that are not paired like this. The interesting part about this algorithm is actually the group equal. Right? We need to group things, and we need to find like which one is green, which I inserted in the other diagram. And it's using one of my, I really like this feature. I don't know exactly when it was introduced, but it's now very easy to write a generator. It's using the iter from function syntax, and it's basically writing a loop. We just take a slice, and we want to return sub-slices of segments that are the same. So every time we find something that's not the same as the current anymore, we create a slice of it and return it. And the next time, because this is an iterator, when we call next on it the following time, it will move on and keeps updating the start and current state. So that's one feature I wanted to show. But with that, we already have our boundary segments. We just put it in a vector, we grouped it, and we took out the ones that were near each other that we cared about. So now already we can move on to making rings out of those. You see I'm here using a strategy pattern with ring maker. That's a trait. That means this one, as you saw maybe on the previous slide, is using linear search. But you can use many different other ones, like binary search, a hash map, or an R tree for, that's a spatial index. Now, this trait has 3 steps. Once at line 46, it's being initialized. On line 48, you just get the first segment, doesn't matter which one it is, of your ring that we're going to form. And after that, we're just going to loop over it, give me the next point, give me the next point, give me the next point. So that's the algorithm, and you can decide how you want to implement that. One implementation is here with linear search. Which is the first one, doesn't matter, so I left that out. Basically what this does, we're going to take a slice, we're going to just do a linear search. Okay, what's my next point that matches the first that matches the head? and then the other part of the segment is what we're going to take out. Let me explain this a little bit more with a diagram. So we're going to keep track of the ones we have used. The first time we want a segment, that's the green one in the second image. That's just the next one that's then being used. And we're going to find the next head. And we're just going to do a linear search over the entire array. And this is maybe 200 gigabytes of data. So that might be a long time, you might think. But when we find it, we'll just swap it to the front. That means our used grows until all of the elements are used. Now, how is this still performing? Let's go. Well, this one, yeah? Is that we know that in our array that we have, when we sorted it, we made sure that we sorted in a way that the data that's near each other in reality is also near each other in the vector. So normally, if you would just sort by x and then sort by all the y's, you would get very long striped arrays. By using Morton code or Hilbert curve, it doesn't really matter. We make sure that everything's very local. So we actually have a very hot loop of iterating over. So we know that we don't have to search far because we started with something that's local. We're just going to not end up far.
One question. So here you're doing a swap remove, or you're not doing a slide of the whole pack, are you?
So I'm swapping this one to here,
Yeah.
right? And the next time we're going to look for the segment that's connected to that one. So we're going to search again, but now from here. So we make a new slice. So the slice we take is getting smaller and smaller. Okay, thank you. I should repeat the question though, but yeah. Yeah, and Morton code is fairly straightforward. You just interleave the x and the y, and then you get a value that's on this curve. Another interesting thing that we can do, and it's actually ends up being the bit that's the giving the name to the talk, is when we work at a global scale, we go have longitude from -180 to +180, and for latitude from -90 to +90. If we want to have the most accuracy possible, then we use all the bits, and we're running ahead a little bit. We're going to use integers for our coordinates. We want to use 32 bits, so we need 1 bit for the sign bit, and then all the other bits are used to divide the 180, and then we get roughly like centimeter accuracy. But for latitude, we only have 90 degrees. That means we have 1 bit less. We need 1 bit less to store this number for latitude, which means there's 1 bit available. Does anyone know what bit we're going to use this for? Thinking? Almost? It's the flip bit. Remember that we flipped our segments? We need to keep track because we want to flip them back as well. So whether the segment was flipped or not, we can store in this segment so we don't have to use more space. Again, an optimization, but not really necessary. All right, to be able to do these kinds of algorithms, there are 2 key factors that are really important when you do anything with geometry, is make your geometry clean and robust, because if it is, we can do these kinds of algorithms. The difference in terms of performance, and this is happened in real life because this happened with the ministry and such, they had some issues with performance. It took 2 weeks to process the data. They first asked me, they first were not clear about like how long it was taking. They just said it took a long time, and I was like, what's a long time? Is it 20 seconds? Like maybe 2 minutes? No, it's 2 weeks. So making sure that you can rely on topology is very important. So what does clean data mean? No self-intersections, no dangling lines. It's just simple features, no repeated points and those kind of things, but also robust. Topological threshold we already talked about. So the topological threshold is when points that are equal are only equal when they're exactly equal. So if there's any difference between them, we just consider them not connected at all. And geometrical threshold, because we are going to do some calculations that use floating points and are imprecise, so there might be floating point errors. So in the bottom right, if you have 0.4, it's very close to the edge of 1 and 2. So some algorithms might say it's on top of it, some say it's above it, some say it's below it. If we just get a geometrical threshold, that's roughly half the unit size, or depending on your map, it's a quite arbitrary number, half. But just make sure it's a little bit above the line so that nobody is confused about that. All right, any questions there before we get into the next section? All right. So the next part of it is data structures. Data structures is what gives you your performance, and it's really important to understand how your CPU works. So what makes your CPU fast or slow? If data is in a register, it's really fast. The latency to access is really fast. Caches are a bit slower, still very fast. Main memory starts to get a bit slower, and disk is just slow. Even, well, new NVMe drives are really, really fast in throughput. They can do 5 gigabytes per second, but latency is still in the order of like 50,000 cycles or something. So like orders of magnitude. So we need to really make sure that it's predictable, that the CPU can fetch the data beforehand, or that's automatically got there because it's next to each other. Make sure it's predictable. Also, because we know that we're going to wait something, sometimes we can compress our data. Right? If we can make our data smaller, we have to load data less. My general rule that it's not based on anything much, but roughly 200 lines of code are fine if you're reading from disk into registers for compressing and decompressing. So if it's half the size, you can spend some time on decompressing it because you have to load less. Or 20 lines when it's like coming from main memory and going into registers. So that's what we're going to do. One important fact here is like there are many databases or libraries that do many kind of things. The problem with that is they always have to deal with generic data. We almost always dealing with maps. There's a data model. We know our data. We can optimize accordingly. So, but let's start from the standard idea of how you would implement a geometry with some attributes features. So you would have a coordinate, an x and a y. It's in a ring, so just a vector, of course. I've seen a linked list, and every ordinate was allocated separately. I'm not starting there. That's too bad. At least start with a vector. But you might have like these attributes, like the purpose of the road, the material of the road, the accuracy that it was captured with. So we're going to make this better. The very first thing I would want to change is to not use floating points for our coordinates. So we're changing that to I32. We know the extent, right? We already saw, for example, with the globe, how much data, what the ranges are. We know what our minimum precision is that we need. We can just convert it, but also using integers, we don't have to do with floating point errors. The integer is very clearly, it's exactly the same, easy to deal with. It doesn't even have to be I32. If it's I64, it's fine. It's still better than a floating point. It also halves our data in this case for the geometry. The next thing I would do is replace the purpose and materials. Don't use strings as much as possible. The thing that we're going for is no allocations per feature. Again, we have like 200 gigabytes of data. We have millions or sometimes billions of objects. Doing allocations at a one feature basis is just not acceptable. So we use enumerations, and we drastically reduce the size of the data that the attributes take up. Next time is we're going to stick with the attribute for a little bit. And again, this is a bit, so it's less necessary, but it's fun. So we had attributes, and maybe you have a purpose, and you have 8 different types of purposes and 8 different types of materials. That means we only need a small number of bits. So we can just take 3 bits for the material, 3 bits for the purpose. And we also changed actually the accuracy to integer, because that range, like again, we know the range what it can be. We don't need the full floating point range. But now we can squash them together with bit packing and just use one U16 to support all of them. All right, this is like getting to the more important stuff. we are completely changing. Okay, let's just take this slide. No. Okay, sorry. So we're completely changing our data structure. But before we had one ring, now all the structures have an S at the end. It's rings. So this is columnar data. It's very similar to like NumPy or PolarRS, and this gives us lots of benefits. But mostly it's just all flat data. All the X coordinates, all the Y coordinates. It's very easy to maintain, and all the attributes. There's been many companies that have also gone through this transformation. So Photoshop, for example, with their RGB or like whatever they exactly store, had to do similar transformation just to make it actually less complex code, but also just easier to manage. If you want to write this to disk, it's just one straight like dump of the file. So what this like really implies, like before we had like one feature that would still, like one factor of all the features, but everyone would still allocate the coordinates. Now for all the features, we just have 4 arrays or vectors. One for the x's, one for the y's, one for the start indices, and one for the attributes. One last optimization that's really important is we don't need attributes. Right? We're just dealing with geometry. And now that our files and how our data is stored on disk is in this columnar format, we can just not read the file that stores the attributes, or not read the Z values of the file. Again, this we like if we started with 200 gigabytes, not reading the attributes, that's generally half, just 100 gigabytes that you don't have to read. Now we're getting again into more of the bit stuff. Where we have, previously we had 4 bytes of integers per ordinate, and that's not optimized, so we want to make that smaller. We're going to use like little endian base, but it's usually the libraries are called variable integers. It's very similar to UTF-8, where we're going to have 1 bit indicating whether there are more bytes to come. So this is a small number. It just fits in 127 or something. It's fine to store with just 1 byte. We don't need all 4. Here we have a number that's a bit bigger. The first bit indicates, oh, there's the next one, oh, there's the next one. What this means, for very large numbers, we're actually going to use 5 bytes to store a 4-bit integer. So to deal with that properly, we need to make sure that our integers are very small. There are 2 important ways of doing that. One, we could just make sure that they are all positive and small to begin with by tiling our maps. And for every tile, you just give the relative position to the tile. But that has a lot of implications on your data. So a bit more generic approach is we're going to do delta encoding. So that means generally our polygons, all the points are close to each other. So if we take the delta between the 2 axes, the difference is going to be small. An implication that it does have is that some of the integers, like half of them, you expect them to be negative. Negative numbers start with high bits being set, so those are not great for our compression with the variable-sized integers. So we use the zigzag encoding to make sure that small negative numbers are also small, few number of bytes. So you can see it here on the right. -1 is mapped to 1, 1 is mapped to 2, -2 is mapped to 3, 2 is mapped to 4. So that way we make sure that all the integers are very small. So yeah, in general, prevent reading things. Like if you don't need to read it, let's make things faster. Compress things so that, again, disk is our main thing that makes things slow, and prevent especially any allocations per feature. All right. Now, what do you do with this information? Where is this? This is a chart I have made a while ago, where how can you evaluate what a company is like, and if you are a company, how can you improve your system? Generally, there's like a level 0 like this companies, like let's not care about that. Like Python with SQL is a good solution for many use cases, but I would highly recommend not starting there because you get stuck. It's much easier, like there's no evolution part, no upgrade path. And I also get down to explain a little bit more why Python, specifically for mapping, is not a great choice. But also with SQL, you end up tying yourself to a certain performance and end up needing to scale, getting a team to put things on AWS. Also, I think it was Amazon or Jeff Bezos that's saying, like, never have shared databases. But if you're a Geo company and you take yourself seriously, you want to take ownership of your core tech. So I would highly recommend at least starting with just basic vectors, basic hash maps. It's not too difficult. Spend some time on your geometry. If you don't want to do that, there are great libraries, maybe GeoParquet or GeoArrow, that do most of this columnar data for you. But over time, you want to be growing your, like you're going to have some low latency API where you need to very quickly respond or you need to compress data a lot. Over time, you keep having more products that require higher performance because we are dealing with this much data. So you start building your war chest, and eventually, like this is the part we've been talking about now, but you get like to have a full ecosystem of tools and libraries that you can lever and that allow you to make new tools and new libraries very quickly because you've built up this equity. Right, so quickly feeding back to why I don't think Python is great for specifically mapping is because, Python is great for many areas, and often because prototyping is so fast in it. I would argue that prototyping with the tools for mapping is much, much faster. I've seen tools in Python being developed over weeks that I can write with FME, where you just drag some operations together, you put the data in, you get it out immediately. It's much more fast, much faster, and the UI and everything, it's greatly supported. We have other tools like QGIS and dbeaver to access the database or any kind of geometry file format. So that's why you don't need Python for prototyping. You can just do your prototyping here and then write it in a decently performing language where you can just opt into optimizations whenever you get a chance to go there. In summary, we saw algorithms, some data, make sure it's clean and robust so that you can leverage the topology. We saw data structures, columnar data, no allocations, maybe you use integers and enums for everything. One notion I didn't mention before, like you might have strings, by the way. So like addresses or postal codes. Use an allocator, just at least make sure you can just allocate a large section of data beforehand. But in general, integers and enumerations. And lastly, separate your prototyping from the code and use a language with opt-in optimizations. I would suggest Rust. And generally avoid getting stuck into one spatial database because maintenance and other performance and scaling questions becoming an issue. All right, that's it for my talk. Thank you very much.
Not so fast. Let's take some questions. If you have a question, please raise your hand and I'll come give you the mic.
So considering the variable length integers and the indices, like the indices are just for the specific like polygons per se, or like how, can you index into where each integer is? Like I don't know, kind of curious about that.
So if we ignore the variable sized integers first, so like here we would have one triangle, right? We start with the index 0, so that points to the first one, and we know the next ring will start at index 3, so 0, 1, and 2 form this one triangle. For the variable sized integers, that's basically the same. We just point to the first one and to the next one. then that way we can still get the slice of the entire U8, and that entire slice is, of the ring is being processed together in one go. Does that make sense? Yeah, so just you basically do the same thing, except you index the U8s instead of the integers.
So I think two questions. One of them is with the variable length integers. When we're actually doing the algorithm, there's going to be a lot of extra processing required to go from this var int to some integer that we can actually use. Like, how does the performance benefit compared to the size? Sorry, how does the performance cost compared to the size benefits?
Yeah, so how does the performance impact? First, one thing I would like to say, just this is one of the big things. This is much less important, and you need to determine whether it matters for your use case. Sorry, could you? Oh.
If you want, I can give you a piece of trivia. I can give you a piece of trivia to kind of answer your question. For very memory-bound processes, I had a friend who was doing something that is called lattice QCD, where you have to do operations on 3x3 matrices with a particular symmetry, and he was doing this on GPUs. So he used the symmetry of the matrices, and instead of feeding to the GPU the full 3x3 matrix, he just passed the first two rows and he reconstructed the third one on the fly, plus 33% improvement. So it really strictly depends on what you're doing. If you're memory bound, it pays off to do what Sjors is showing.
Yeah, exactly. When you're using this, there are libraries that you can use. They use SIMD. They're reasonable in performance, but you're very right that this does take time to compute.
Follow-up question?
Sorry. So the other question is, so this data structure seems like something that we have to build every single time that we want to process the data. What happens when you want to write to this? You don't store data in a database like this, probably, because I feel like it's really hard to modify it. You have to change move the array forward if you want to add a vertex, for example.
Right, yeah, so because if we want to insert anything, we're kind of screwed and have to copy the entire data set. That's not great. Two things. Very often when we're working with maps, we want to immediately write to disk again because you're editing, you're making changes, and you want to have every different state. The other thing is I'm using a vector here. Vectors are not always great. Like as soon as you get to like page size or something, combining a vector with like contiguous array that you can at the end have a pointer to another array or those kind of like rope data structures allows you to have large sections of contiguous data, but able to like, okay, I do need to make a change here, then you just change the pointer only for that large section. Get things like that. And for HashMap, you have also similar things to just have immutable data structures. But in general, it was my experience coming from C++, where I am much more able to do mutations and such. But we found we're just doing conversions. We're just analyzing what the data is and getting like a small output set that we actually don't need mutable data.
So data is not stored like this. Is it stored like this in disk, for example?
I would store it exactly like this on disk. That means you can memory map it, right? So you just leave it to the OS to determine what needs to be in memory or what not. But you can directly index into the thing and you don't. Thank you.
Great question so far. Let's keep them coming. All right, that's it, I guess. So I'm just going to ask my stupid questions. So you have a background in aerospace engineering, right? And
Yes.
I think you used to work on, I'm very excited about space stuff, so obviously I'm going to ask about that. You worked on what exactly?
In aerospace, one of the final projects was getting us to Mars as soon as possible. And what is the technology and by what timing can we get there? The goal was to get it in 30 days. I think we ended up with 70 days using some nuclear reactor to generate energy and fusion-like plasma-based engine to propel us. But that project, like it sounds crazy, but actually 2 or 3 years later, NASA, I think, did exactly the same study and came up with basically the same using RFC FRC, filter reversed configuration engines. So yeah, that's what I did.
That sounds pretty cool. If you have any more questions about that, don't forget to find Sjors after the talk. Right. How did you get into computers and programming?
Yeah, so like I was doing aerospace, and the faculty was very focused on just planes, and I thought there was also space in the name, and they thought like space is not really a thing anymore these days. Yeah. So I noticed I was good at programming, so I wanted to make the switch. And geomatics was a study that had like an overlap with computer science. So it's half computer science, but half is like a completely separate field where we're just analyzing data and not even programming, just using those tools that you saw before. So that's how I jumped in. I had been programming since primary school when my mom taught me programming with super logo and up, left, right. But yeah, like at university, like I've been building websites and things and games in my spare time. I noticed at university I was good, so I made the switch and ended up with mapping and really liking it.
You're skipping ahead. My next question was going to be, what was your first programming language? It sounds like it was Logo.
Yeah, super logo. Just the very first one, just black background, the green thing, barely recognizable that it's supposed to be a turtle. But yeah.
Shots fired. What was your first real programming language?
I would say Java. So we got seriously. Well, not HTML also. Yeah, I think Java, that's what we're taught at university. So we had a very object-oriented education there.
How did you get into Rust?
In Rust, so like at the start of my career, I was very much into C++. I knew everything about C++. And we got into this in Woven, in the safety-critical situation where if you make mistakes, things blow up, and yeah, there are serious consequences to making mistakes. But we also, again, we need the performance of a language like Rust, so that's why C++ is generally the standard go-to. But we also had a team of fairly junior contractors. So I introduced Rust partially because I also had just been looking at it for 2 years, so I was interested. But it was really great for our team because for the people joining the team, I'm fine with them not getting it to compile. The compiler will tell them what to do. It's more important that they don't, like it's hard for them to get it to compile, but it's also hard for them to get it wrong. So what they produce is like of some quality that I can work with. And yeah, for this situation, that was really great. I think all the teams liked it.
What was something that was really difficult for you to learn when you were learning Rust?
So for me, lifetimes was actually not so much as a problem as it's usually said. Coming from C++, I had a programming style that's more C-like. It was very similar to what Rust is doing. So I did not run into many of the lifetime issues. What I struggled with more is a little bit what I mentioned before with immutable data, to get that to go right until I realized, okay, just don't. And the other thing is with unsafe code, where you generally don't have to write it, but that one transmute, the problem there is that it's much more unsafe than even C++. Like all the guardrails are there. There are no guardrails. There's no concept of guardrails anymore. So it's really hard to be sure that what you're writing in unsafe code, that it's actually correct and actually safe.
And what was something that you really liked when you discovered that made you really, really happy?
Really, really happy. So the biggest advantage that I find is that we don't debug things. We write our things, the compiler compiles it, we're done with it. We write our tests to make sure that the logic is correct. And there's no time where there's very limited time in debugging. Like you don't have stories where like we were searching for weeks to find that a floating point of 64-bit turned into a 32 thing. Like that doesn't happen, especially if you're careful. Don't use as conversions, just use like try from. Just not having to debug anymore was definitely a major advantage.
This does sound like Haskell to me.
I'm not against Haskell.
All right, thank you for this presentation.
Thank you.
Thank you for coming. Don't forget that there's beer in the back until 8, so we have 5 more minutes.